So, week 8 of our course FAST, that is femtosecond, fundamentals of attosecond science and technology. We as always bring it to you from here in Chennai, IIT Madras, with our team of colleagues from both the IITs, Madras and Tirupati. And we will in this lecture jump into the next important steps for this course based on the same set of references I have been usually using using for this for this course so far. Femtosecond laser pulses by Roulier and fundamentals of attosecond optics and principles of optics. Thanks once again to Professor Trebino for lecture materials and inputs. He may even join us for a guest lecture sometime when we cover metrology of pulses. Let's hope we can work that out. That would be great. He is the inventor of these primary techniques for unambiguous and complete characterization of femto and even attosecond pulses subsequently. So, we will as always recap a bit of our earlier lessons, but I will do it quickly this time. So, we have made a very good headway to femtosecond pulses, the time and frequency domain description, concepts such as instantaneous frequency, interpretations of the phase terms. We will continue doing that further in this class, but we looked at group delay and group delay dispersion. And then we will in today's lecture and this week we will explore few more details which are really important for this conceptual development, not only of femtosecond pulses, although we will make that the basis for our understanding femto and attosecond, and indeed all electromagnetic pulses that we will we could encounter. If you look into radars which operate in the microwave, exactly the same concepts apply. In fact, a whole lot of these techniques are already well developed in the microwave regime, and clever scientists, physicists and engineers literally figured out ways to redo that at going from gigahertz to tera and petahertz time scales, and now in time scales greater than petahertz going towards exahertz, which is attoseconds and extreme ultraviolet. These concepts remain pretty much the same. So, you learn it in one domain, you're good for others. Techniques may vary and the concepts remain, metrology techniques of measurement will vary. In fact, sometimes one can even port these from one domain to another. Okay. So, with that little preamble, let us do a quick recap. A typical pulse looks this way. We have flashed it almost ad infinitum in this course, but it is a really important view to keep in mind, and the fact that the electric field has a real amplitude square root of I of t, a fast varying phase factor, the carrier wave which oscillates underneath the envelope which is marked in real space by square root of I of t, as well as a slow variation of phase which is phi of t, which is slower as compared to the variations on the carrier frequency. We can club the the terms other than the carrier frequency term omega naught into a complex amplitude E of t, which is the square root of I of t and e to the I phi of t. This essentially we have removed the fast varying stuff underneath the carrier, underneath the envelope, that is the carrier oscillations are not present in the complex amplitude, but everything else is, and from this the real amplitude can further be filtered out as the square root of I of t. So, this is how a Gaussian pulse with a constant temporal phase function phi of t, the constant can is not absolute. The constant is we can set it to 0 or any value, since it is constant across time, it does not really matter. But then we also understood that we have an equivalent description of the same pulses, equally complete, equally legal and legitimate in the spectral domain. So, the intensity and phase, which we should appropriately have called temporal intensity and temporal phase, are now replaced by the spectral intensity and spectral phase, and Fourier transforming this real pulse E of t, which is a half square root of I t exponent of I omega t minus phi plus the complex conjugate to emphasize the fact that these fields are real. When Fourier transformed yield us two pieces, both of which contain identical information, a spectral amplitude the square root of s of omega minus omega naught. This is omega naught being the carrier frequency, and the exponent of minus I times phi in the spectral domain, the spectral phase function phi of omega minus omega naught. So, this goes on to say that for a complete characterization of any pulse or complete knowledge of a pulse, if we can in the spectral domain measure out either the square root of s of omega or s of omega itself, does not matter, either way we get the same info, and then figure out a way to measure the phi, we know everything, right. And since these two functions are the same, the second term essentially is owing to the complex conjugate, which keeps things real, because we chose the time domain to describe the pulse in a primary sense, right. So, this led us to again describing an amplitude complex frequency domain pulse field E tilde of omega, which is the square root of s omega. Note that we have done away with the carrier frequency omega naught in this term. So, this spectrum here is centered about 0 because omega naught is just a number, and as we always have emphasized, for well behaved pulses, this is we can treat them this way. It is say for conceptual development, mathematical convenience, we can work it out using this relatively more compact expression, where S is the spectrum and phi is the spectral phase. And essentially now to emphasize the fact that we have now alternate ways in which to represent the pulse. We have E of t, the complete descriptor of the pulse in the time domain, including the carrier frequency, script t of t, that is, and we had then E of t, which is a different function, which was the complex amplitude in the time domain, owing to our preference to use the complex notation. And when Fourier transforming this, we got two types of functions, E tilde of omega, where the information about the carrier frequency in the spectrum is retained, whereas here the unscripted E tilde of omega essentially is centered about 0 frequency. They all contain the same information, both in terms of the amplitude function, which is denoted here by the intensity, which is the spectral intensity, which in all these cases are the bold lines, as well as the spectral phase, which is equally, if not in some sense is more important, the spectral phase function, which refers to the right vertical axis. Okay. So, we often use only this component in describing the pulse, but then the whole idea is to work out whatever we would like to work out and keep things consistent throughout and retrieve the real field in the time or the frequency domains, because electric field is real. We can write the spectral intensity and phase functions in terms of the electric field E tilde of omega using these relations. We looked at how a very plain vanilla Gaussian pulse with constant phase looks like, and we understood that it is indeed the spectral domain which synthesizes these pulses into what is observed as a single pulse in the time domain, in the sense of a constructive interference when phi of omega is constant across the various constituent frequencies. We have 6 of these here, and the interference constructive interference about t is equal to 0, which is a favorably chosen reference point on the time axis, is present. And then we can define so called instantaneous frequency, which is the instantaneous time derivative of the entire phase factor omega naught t minus phi of t, which yields us for a frequency factor omega naught minus d phi by dt. Note here that phi is measured in radians. So, d phi by dt is radians per second, and the angular frequency angular carrier frequency, the angular carrier frequency if you wish is omega naught, and the left side is instantaneous angular frequency. We can also express this in terms of the instantaneous cyclical frequency, or just simply instantaneous frequency nu instantaneous, nu naught minus d phi by dt. Of course, here factors of 2 pi appear owing to the way in which we have defined phi, which for example has units of radians. So, it divided by 2 pi radians in order to set things in order. So, the concept of then group delay came in sort of naturally, because d phi by dt is a component of the instantaneous frequency. Now, d phi by d omega, the same phase function, but in the spectral domain, when you measure its slope in the frequency domain, gives us a quantity which has units of time. This is what we call the group delay, and based on this we went about looking at two Taylor series, one in the time domain, where phi of t is a function which is required to describe a pulse, but it is yet to be measured. So, therefore, it is not a priori known, nor is the amplitude known for that matter. But then in the case of amplitudes, we have reason enough, considering this is a pulse, to adopt shapes which are close to Gaussian or secant hyperbolic, or maybe sinc square or whatever, based on, which should be based on good physical reason, or sometimes even say mathematical convenience. Whereas in this case, we do not have a reasonable way to presume that these phase functions have forms which are mathematically either elegant or even convenient. Of course, a flat spectral phase is always a possibility, but then we can consider this Taylor series as a measure of increasing deviations from a constant temporal phase, and phi naught is constant temporal phase. We saw a Gaussian pulse which had only a non-zero phi naught and phi 1, phi 2 and others being 0. So, the next higher order detail is has a coefficient phi 1, and this is one term which is of importance. We even interpreted this as something related to the instantaneous frequency, and we will interpret the term related to phi 2, so the second order term in time, as something going further. The derivative of this, of something related to this instantaneous frequency as well, will start playing a role. So, this is a sort of, you can view this as a measure of deviation from a constant phase to linear phase to quadratic phase. If you are comfortable dealing with all these three terms, all the higher order terms with any significant contributions would measure the deviation from this presumed quadratic model for the phase. Okay, so that is a good point where we can jump into the current lecture from. In fact, I will even before going into new material for this class, continue further to begin the discussion with this spectral phase function phi of omega, which has the 0th order phase, about which we elaborated in quite some detail in the last two lectures. This is the 0th order phase. We call this the absolute phase, the initial phase, and as we saw in earlier lectures, this is important for pulses which have a significantly small number of cycles, maybe 1, 2, 3, maybe even 3 is too large for it, underneath the envelope or even the full width at half max of the envelope. Now, phi 1 is the first order term in this Taylor expansion. Much like phi of t, we do not know much about phi of omega, except that maybe, or we can call a pulse with just a non-zero phi 0, that is only the non-zero Taylor coefficient is the 0th order term, as the best pulse, the most ideal pulse. We will give it a name when we take things forward, but deviations from this would be a pulse in which we have non-zero and significant phi 1, but maybe negligible or even 0 phi 2, however we wish to phrase it, or pulses where phi 2 is significant and the higher order terms are not. So, but then the way to understand phi 1 is what we already saw. D phi by d omega is the group delay, okay, and the derivative or the variation of d phi by d omega, that is the derivative of this one taken once again, is the dispersion of group delay or group delay dispersion. So, phi 1 and phi 2 are important, and of course, we have red lettered group delay dispersion because this is going to appear again and again in this course, and will indeed stay with us all throughout as something that happens during the propagation of a pulse through a dispersive, again underscore, that is why the media are dispersive media, or even media with some amount of optical nonlinearity in them. So, the 0th order phase, the absolute phase as we have called it, we also gave it the name carrier envelope phase, as the case may be. The 0th order phase is the same whether expressed in time of frequency domain, because it is just a pure phase factor. In that sense, it does not matter in which domain you measure it, you do not have to go through the additional step of maybe converting it from one domain to another. But then if we focus our attention on the view graph to the right, where we have the scale going all the way from just about 5 femtoseconds on either side of 0. Here each cycle is about 3 femtoseconds long. So, this is a typical pulse from a 800 nanometer a laser which produces femtosecond pulses centered at 800 nanometers in wavelength, which is typically a medium called titanium sapphire, by far until recently the most popular medium for producing femtosecond pulses. Then you essentially get, for a certain way of quantifying phi naught, when phi naught is 0, you get this dark line pulse over here. Okay, this is a place where maybe I can emphasize things a little bit. This dark line pulse, where visually it is obvious that the maximum of the carrier field underneath and the maximum of the envelope, they both, the two maxima are in sync. So, we take this as the reference for 0 of phi naught. So, that is how we set a definite scale for measuring phi naught. Okay. So, if we accept this definition, you are free to give other definitions yourself, but then for now this is what we have used. If we now have a pi over 2 phase shift, okay, of the maximum of the envelope, and it is the nearest maximum to it of the carrier, right, which would be related to the pulse with 0 phase shift, the same way a sine, cosine and sine function respectively are related. So, we could call the 0 shift pulse as a cosine pulse, and the pi over 2 shifted pulse as the sine pulse. So, these two, if we subscribe to this definition of the phi naught phase phi naught, have ostensibly different shapes of E, as I like to call it, shapes of the electric field, right. So, remember that the 0th order term is the shape of E term, if you like, right. So, that makes a good point. Whereas, if you see for these pulses, I mean these are for a practitioner, a single cycle pulse is lot of effort. In fact, it takes special efforts to produce this, about which we will have something to say much later, or not much later, sometime later. Whereas, if you see this pulse, which is also not trivial to produce, which has a full width at half max of about, let us say, somewhere here. So, this is about 15 femtoseconds. I messed up my highlighter. Oh, what am I doing? Okay. So, let us say about 15 femtoseconds in width as defined by full width at half max. For these pulses, the differentiation between the 0 and pi shifted pulse visually does not seem to be as significant. Okay. Although, if you peer into it, you can say that, hey, look, in one of the pulses, the envelope of the carrier and the maximum of the carrier and envelope are is on the so called positive field side and the other is the negative field side. But what is positive and negative? It is just you can say these are just arbitrary in definition. In both cases you see the field is meeting the envelope maximum, but then there are so many cycles underneath the envelope even by the time you get to these pulses, which are about if in this case it is let us say 15 femtoseconds, okay, or here it seems we have called it a 4 cycle pulse. So, approximately 11 to 12 femtoseconds, which is pretty short actually already, right. The contrast or in some sense between these pulses becomes quite different. All right. I mean, I made this point, but I do not mind spending a minute more to make this point once again, that in this case, if we started with a pulse literally of this type versus a pulse, I am not drawing things to scale because just in the interest of time, so bear with me, but this is just to make a good point, as good a point as we can. That is, so this is the 0 level here, this is the 0 level over here. If I do this, now the point is that, okay, this is where I must maybe make a 2-minute pause to ask you if you thought about how you can characterize or differentiate these two kinds of pulses in a laboratory scenario, wherein I threw in this thought, not thought, it is a fact. I am here writing down the real electric field, not one using complex notation, that if I integrate over the electric field over sufficiently long durations, I mean in this case you do not even care because the duration over which the field is appreciably non-zero is pretty short. I mean the cycles here set a scale of the time axis by themselves. On the time axis which is here, and this is, feel that the scale on the time axis is some sort of self calibrated because of the fact that except for the 0 which we can peg to the maximum of the envelope. Oh sorry, that is in the maximum of the envelope in this case. Sorry, my sketching is a little poor on this side. So, maybe it is enough for me to show one of the envelopes, keeps the whole diagram neater. Good. Okay. So, either way, the point being, now how do I differentiate these two pulses in terms of measurement using a measurement technique, considering the fact that unfortunately this is true. Any slow detector would measure something like this. For this, on the time scale of the pulse, it is on for an infinite amount of time. So, very well with making these little plots which you can do on MATLAB or Python in 10 minutes, write a simple program for, but then how do I measure them in the lab? Can I differentiate these two? Because I showed you this in the next lecture that not just Professor Krauss, his group, but a group from the University of Jena led by Professor Gerard Paulus actually invented a technique to discriminate or differentiate this entire set of pulse fields all the way from 0 of what we called phi 0, which is phi 0 for us, the relative phase difference between the maxima of the carrier and of the envelope and the nearest carrier maximum, which is why we call it carrier envelope phase, for the entire 0 to 2 pi, or in values that the carrier envelope phase or phi naught, the initial or absolute phase here takes, we essentially have a technique that can fingerprint each of these pulses, right. So, so there is a technique which is shown here, but the whole point is that we can measure out the fields like this. Here is a real true measurement of the of a pulse. You can try and visualize its carrier envelope phase, but I wouldn't actually. I mean, you can visualize an envelope here, but vertical scale is not amplitude. Please note that here. This is not field amplitude. It says electron kinetic energy. So, that is another matter. It is actually the derivative of this field. Let me not go there for the moment. It is some vertical axis, but you can, the point to make is you can indeed measure this out. This is one of the big successes of attosecond physics, but there is a technique which somebody invented to essentially map out and read out the phase of, read out the C phase or phi naught for each of these pulses, of these reliable and repeatable pulses that a laser can emit with controlled phi naughts or controlled C phase. Okay. So, let us come here, that is to say you can give a score in terms of phase score. For this pulse is 0, for this pulse is pi over 2. There is a whole sequence of pulses between 0 to pi over 2 on this scoring, on this with some score on the scoreboard, going all the way to pi and 2 pi wrapping back to the 0, right. How do we get a measure for this phase? So, this was the question that we had in the previous lecture. So, any thoughts, any ideas?
First figure looks like an even function, and the second one looks like a what?
Yeah, that's, we called it cosine and sine. So, it is, you have given them good names, certainly that is true. But how do I get a measure for this in a laboratory? Using slow detectors. This is really a puzzle. Someone solved this puzzle. That is all I am trying to say. So, I am just trying to pique your imagination a bit to ask you what can happen, or what could be a strategy for that. It is by no means a trivial matter, but you are all smart young people. So, I am pretty sure there could be ideas. For those who have seen this in the earlier lectures and had a few days to ponder over this, right from the time you wake up to sleep to maybe even in one's dreams. You know that the structure of benzene, appeared to somebody in his dreams, and he even won a Nobel Prize for that. Okay, this will not fetch a Nobel Prize because someone already discovered it, but that apart, you would have grandmaster level inventiveness, let us just put it that way, if you figure this out. Yes, Pratik? Okay, I am still not going to give you the answer because we still have time. However, the fact that Ritesh observed is an argument for symmetry on either side of the 0 of the time axis. One of them is even, one of them is odd. That's I mean, although it is restating the obvious, but often clues lie in the obvious, why not? Okay, so now since we took a step in that direction, I am going to just put another thought in your mind. How about thinking of things on either side of this vertical axis, on the 0 of the vertical axis. After all, the field has to make excursions from 0 to a positive max, what we call a positive maximum, to a negative maximum. It has to flip direction and then go past a 0 and come back, and so on. I mean, that is the sum and substance of this whole integral being 0, right. So when we sketch a pulse like this, we ought to take care that the area that is under this curve on either side, what we call the positive or the negative, is roughly equal. So this is a, I mean, I would give this just a 2 star out of 5 for my sketching abilities, barely pass. I did not do that well enough, but that is the point. So now think about it from the vertical axis perspective. Okay. So leaving you with that thought, let me move forward. Okay. So indeed it is measurable. If you read this article, you are there more or less. It's a such an elegant idea. It wouldn't be so such a mystery anymore. Okay, but I brought up the fact that this phi naught can also have slow variations in time, either owing to the way the laser that produces these pulses behaves, or the fact that you may choose to modulate phi naught as a slow function of time, right. If it's done, if one chooses to modulate this as a slow function of time, what we essentially do, or if it happens in a laser, it runs randomly, right. Phi naught varies randomly in time, which it does in a laser unless we do something to control it. Then what happens is this gives us a frequency, because any phi by dt, if it is not 0, then it is some frequency. What it is our burden to interpret. So what this essentially does is that it basically defines the offset of the comb of frequencies that such a laser would emit, right, and it's a measure of the deviation of the combs of this frequency nu q, which were q, the integer index, which we got in our earlier discussions, from the deviation of this comb away from the 0 when extrapolated all the way down, right. So that gives us the concept of an offset. So we have a carrier envelope phase, and this frequency, that any time derivative of this, if non-zero, gives us a frequency that offsets this comb, or a carrier envelope offset frequency, right.